Okay. Adapted yesterday seminar. Anyway, very pleased to introduce Sergey Gavrilyuk. He's at Marseille University, and I think it's fitting that he's speaking because he's definitely one of the main contributors to the field of dispersive hydrodynamics. And he gave a talk in at least one of the workshops, but it was remote. Yeah. I think the analysis or the integral systems in Loughborough. Yeah, Loughborough. So he was here in the summer, and he told me by email that he had a dream last night that he would be back in Cambridge. Okay. And I was pleased, and I was pleased to write that his dream has come true. I am so
Mark. Okay. First of all, I would like to thank the organizers of this program. Okay, Naghdi, Mark, Michael. Okay, here, Antonia, and Barbara. Okay, for bringing us, I mean, community dispersive people into the Newton Institute, and for creating creative atmosphere. Maybe it's not very good to say it. I mean, creative. Okay, so atmosphere. So we are happy to be here. Special thanks to the coffee machine in the Institute that never broke down. Okay, finally. Okay, at least during my stay, I know, but during the month it was and of course Newton Institute for Hospitality. Okay, so we'll talk about things I understood recently. So indeed it was okay, people usually speak about motivation, okay? But my motivation was very simple. Just I met a guy who worked on capillary fluids, okay? And he asked me, do you know other those integrals of conservation law for capillary fluids? I told him, no, normally you have just orbital section, momentum, energy, that's it. Sometimes you can define potential flows. But finally, I understood how to introduce helicity, and I will give some basic definitions because not all people maybe know this notion, how to construct for dispersive. I wrote here continuum mechanics. Normally, I should write hydrodynamics, but finally we'll see. I will consider also stress tensor, which is not spherical one. So it's continuum. Okay. First of all, people. Okay. Good. Okay. So first of all, this is so the first part is French, after the and in this case, open here. And the paper of Jean-Jacques Marot was published in Iran in four scientific in the health. And 8 years later, by Moffat in Jones of Mechanics. So completely independent. And finally, what is the definition of helicity? It's very simple. It was done for just parabolic concentration. Suppose you have the parabolic flow, it's the conservation of mass or the density of the velocity, and we rewrite equation of momentum in non-conservative form. So if you introduce what people call enthalpy, H of rho, definition of enthalpy is the following: the H is the E divided by rho, greater than enthalpy. Then you can obtain the
closer to the microphone.
Yeah, so you can, okay, it's better. And then, just by combining this equation, you can introduce the quantity ut multiplied by omega. It is scalar product. Line vector is multiplied by omega, and you obtain this conservation law. And this product ut omega is called local helicity. Is conservation law for local helicity. And then, if you integrate this equation for a special domain, this domain dt is a material domain first, but not only just material domain. Initially, the vorticity vector should be tangent to the boundary of this domain. And then, because you have Helmholtz equation for vorticity, this property will be conserved in time. So if omega is tangent to this boundary initially, it will be always tangent. And French people are more romantic, okay? They call it îlot tourbillonnaire, vertex island, okay? So it was definition of Jean-Jacques Moreau. And finally, again, by integrating this equation, you obtain this stuff. Apparently, actually, a lot of applications of helicity, especially in astrophysics, because you can obtain the same stuff, same quantity for MHD equations, magnetic hydrodynamics, and then you can add dissipation and to see the evolution of helicity. Okay, just to understand more or less this quantity, if U and omega are collinear, okay, it's just non-zero. So roughly speaking, something which is very, very big, okay, and if omega is orthogonal, it is zero. So it's sort of property showing the complexity of the flow in some sense, okay, this integral. Okay. And then, I like it, Moffat wrote, you will see surprised, okay, in 2D I can hope. Okay, so this is main stuff, okay, for example, what is helicity for a Schrödinger equation? Okay, so at the beginning I thought it was zero because omega is zero, okay, but not this. We'll see later. Okay, it so often happens that results we published turn out to have been proved much earlier. Also, the true significance may have escaped attention, as if Moreau's paper and so on. Okay, so actually, Moffat cites this paper. And also, I talked at the beginning, you have Euler equations, you have Hamilton section variational principle. Is a symmetry behind of this helicity conservation law, and the symmetry is called relabeling group, relabeling symmetry group, what this property is. Okay, you know, conservation of the mass, rho multiplied by determinant of deformation gradient is equal to constant. So finally, if you relabel particles, so you consider group of diffeomorphism having unit determinant, okay, the definition of density yield is the same. So this is called relabeling group. And again, it was introduced by my colleague in '76 first, even if now it is attributed to Rick Selman, okay. And Henri, okay, did a talk at the seminar of Jean-Jacques Moreau and about this. So, but it was published in a small English journal, okay, so I have a reference, while publication of Rick Selman was in Journal of Mechanics. So finally, this relabeling group is also mentioned in Zakharov and Kuznetsov's paper. Okay, and then, as I told you, many people continue to study this invariance for incompressible Euler equations, compressible equations, MHD equations, and they found other invariants. For example, consider Euler equations with entropy. You can find Ertel invariants and so on. It is also related with this symmetry group. Again, so I put some people, not all people, okay, Turgenovsky, Arnaud, Hezin, Cottern, Hall, Webb, and Koosses, Chibikov, Oberlach, this application in turbulence, particular Davidson and Ranjan. Okay, so many people continue to work on this. So I ask the question: can I find the same invariant in dispersive hydrodynamics. And first of all, I would like to precise what the helicity is in dispersive hydrodynamics. What does dispersive hydrodynamics or continuum mechanics? And I will consider two types of dispersion. First type of dispersion is the following type. Consider kinetic energy classical way, but the energy is not only a function of density itself, but also the gradient of the density. Okay. Then I have the Lagrangement, Hamilton action, and apply classical method to constraint Lagrangian, because conservation of the mass can never find the mass for operational physics, but constraint. Okay, then you find only Newton's law. So you can find Newton's law, and this system is very popular. Okay, in mechanics, and people say very often gradient type model, or they use those Euler, Korteweg, on the right equation, so in the right for themselves to propose the following thing: that interface between liquid and vapor, and interface is just equation where gradients of density are very important. So gradients are important. Energy of surface is gradient squared roughly speaking. And many people look at this model just like that. Now there is Naghdi, she professor of the university. They derive dynamics of operations and very dynamic terms of operation principle, while on the right formulate static equilibrium. Okay, and then many people make where Marshall said, I like this people. So this is why and pleasure to reach name. Lector Skinov, Sergey, okay, she likes. Then people work on thin film flows, okay, so you will see it is exactly the same system when you take into account capillarity and also high dynamic form of the nonlinear equation, but will transform. But still, there are thousands of people, okay, so I couldn't put it. Okay, finally, let me give an example of this function in form. We saw this many times already, but have the focus in the nonlinear Schrödinger equation. After model transform, you can find such a Lagrange form. Rho is squared over 2 minus W function of rho against rho, and W is given explicitly in such a form. Okay, so it's interesting to, but you know perfectly that curl of U is equal to 0, and Nicolas asks me, okay, what happens if omega is 0? You'll find something like that. Okay, now the next example is example of capillary waves. So we have thin flow, for example, on inclined plane, and then in this case W, very simple. Again, function H, it could be GH squared over 2, or more complex polynomial, because people use for thin flows what they call disjoining pressure. Okay, so we change f of H and the same quadratic dependence on gradient H squared. Now we see here I replace rho by H, so every time it will be or density or maybe the depth of fluid film. It's the only difference. Okay. So perfect. And just a small movie to understand what happened. For example, with capillary fluids, so we have a flow of a thin film of inclined plane. Okay, if we are taking into account, and dispersion relation for this capillary model is such that it is not bound, phase velocity is not bounded. So we see clearly appearance of precursor wave, highly oscillating wave. Okay, typical solutions of system with gradient. And now the second class I will consider, so it's quite generic, okay, the case of fluid where W potential depends not only on density, but also material derivative of density. So, and always we need Gaussian invariant systems. So this is why it's not just function of partial derivative of rho with respect to t or gradient of rho. It should be combination, Gaussian invariant combination, full derivative of density. And of course, usually, I mean, because you have time inversion, it depends on square of the rho over dt. Again, yeah.
To go back to steady flow, surface tension.
Yeah. Yeah.
Doesn't that smooth out the oscillation?
No, not indeed. Capillarity introduces distribution relation which is not bounded, so it can have ways propagate this different velocity for small, okay, for large wave number. So the theory is precursor. What is important for capillarity? So it's not smoothing because when you have motion, because stationary configuration. So it's then this is combination of motion and damping at the same time because you have inclined plane, you have force, okay, driving force, and then in this system we introduced, of course, friction. So we have such a solution for such a. So I'll give you the paper. Okay, so for example, what are applications of such a model when potential depends on rho over dt? Again, we can think about Serre equations. Again, equation of Nicolas, 2D flow, vortex is orthogonal. What happens? So nothing here, but we'll see. And also equations of bubbly fluids. Imagine you have incompressible fluid, you put gas bubbles, they oscillate, you can derive W of such a form dependent on the rho of the T. Good. This example of Serre-Naghdi equation, okay? So we have just 2D flow, rho I will replace by H, and X is X and Y transpose, Q, okay, average depth, average velocity, horizontal velocity, and W is a potential. I don't call it internal energy because it has sign minus here. This part H over 6 dH over dt squared is the part of kinetic energy. So you consider depth average part, this depth average velocity plus this energy and minus potential energy. But what happens, it's much more easy to work with such a potential because, okay, we'll see. This is typical solutions for systems where one-dimensional solution, for instance, where W depends on the rho over dt. So dispersion relation is completely different. In this case, you have bounded sound velocity. Okay, and this typical problem, Gennady was first to consider this Riemann problem for Serre-Naghdi equation, and here it has this magic number 1.8. Okay, Gennady used, okay, because it corresponds to solitary wave of maximal amplitude. Amplitude is 4.78, and the reason to put here Riemann problem is 1.8. So you see here typical structure, okay, dispersive shock, okay, velocity of dispersive shock is larger than velocity of the shock when you consider just Serre equations, okay. Black line is solution of the Serre equation, and you have a shock, reflection wave, and then classical dispersive shock. So the solution is completely different. Okay. Yeah, the relation is very simple. This is two solutions. There's no relation. Okay, I mean, reflection shock is exactly the same. Yeah. Yeah, I put together two solutions. I mean, if you use Serre-Naghdi equation and Serre equation, and you want to describe reflection wave, you see there's no difference at all. Okay. However, the dispersive shocks, okay, it's present, so it has large oscillations, and also velocity of the dispersive shock is the velocity of the solid. Not indeed. I mean, time and say, because you can see that the velocity, shock velocity, is smaller than the velocity of the solid wave. And you consider large time, so you can see difference. It looks like, but it's good. Kilowatt, yeah. Classical then break problem for thermal equations and for Sergey equation. Yeah, exactly. Yeah. Yeah, initial step is okay. I forgot to mention it. So on the left, it has 1.8 meter. Yeah, the right 1%. Okay, and velocity is 0. Okay, for both. Yeah, velocity 0 initial. And this is just H. So yeah, so it looks like as if yeah, but it's not. Yeah. Okay, just to illustrate that properties, dispersive properties are completely different for these two classes of equations. And now let us begin with Lagrangement fluid mechanics, as Tom explained me. So this is what I will use now, okay, because of you. So consider classical application, small x equals capital phi of t and capital X, okay, capital X are Lagrangian coordinates and small x are Euler coordinate motion, okay. Okay, now introduced by F gradient of deformation. So phi with the x, okay. I will denote also like it's small x or capital X. And then classically, if you consider the evolution equation for F, okay, d over dt as always material derivative, df over dt is equal to u with x, f, okay. And velocity u is just partial derivative of phi, t, and then the inverse capital X, phi, okay, classical stuff. Okay, now let's classical stuff. I will consider material surface. Example. Hi. So, wait. So I will consider the vector E. I, example, origin I. So I is just a normal vector. Let me consider another material surface. Okay. Material surface. Consider vector A. So intersection of the two optical surfaces coordinate line. There's no coordinate line A. Okay. Tension vector is line. A directed A is low. Okay, now so I can write evolution of this And evolution of this vector is called basis vector. There are two for basis vector. Basis vector. For example, how can I write evolution equation of I? So a simple equation. Then I can partial, but I can gradient. Every equation I of religion I feel it will be equation for basis vector. And because the gradient of Lagrangement coordinate, so we have symmetry if I over the x is equal to I over x 1/4. And then finally we can write this equation I see material derivative I over I. So then the geometry is the least derivative of covector of one field. Okay, 1/4. The derivative 1/4. Okay, and now the lemma. Okay, I need also evolution equations for this vector, basis vector, and now lemma. Let this definition EI is natural basis, EI with upper index natural co-basis. Then we can write that basis and co-basis are related with this relation. So EK is low index divided by term interface is equal to vector product of two co-basis vectors. And also the main stuff is the following. If I derive, I take divergence of EK divided by term interface is 0. Okay, it is very simple to capital S is definition rate. So, for example, if you take basis vectors, okay, you take determinant of mixed product, okay, and this is the determinant of F. Okay, if you take covectors, you take mixed product of two covectors, it is one with determinant of. Okay, so divergence is 0. It is checked immediately because divergence of vector product EI EJ is divergence EI EJ minus inverse, and because EI are gradients, okay, so sorry, it will be curl of EI. I will, okay, to precise, okay, so divergence EK of determinant of F is divergence of vector product EGT, also like curl, but EI are gradients, so 0. This is also 0. So automatically we have divergence of the vector is equal to. And the fact why people use why I'm using the word basis for basis, because it's just by definition. Basis for basis, the definition is the following: the product of the vector of co-basis scalar product by the vector of basis is delta ij Kronecker, and this is direct case. So dxi or dxj is delta ij is equal to this one. So we introduce basis for basis, and finally divergence of this stuff is equal to 0. Why is this necessary? Okay, again, just what I already explained. So we have initially, for example, plane x bit is equal constant. You have initial co-basis vector orthogonal to this plane, and then you have motion, you have transformation of this material surface, and finally, E beta space always orthogonal to x beta, but the material surface is deformed a little bit. Okay, now the following result, we have already proved this because what F is, remember, it's just E small x over the capital X. So F divided by determinant of F are columns of this vectors I proved already, divergence 0. And then, in the same way, I can find evolution equation for F divided by determinant of F. So it's just the same computations. And if I consider now columns, so this of F divided by determinant of F, so this vectors EI divided by determinant of F, first of all, for this capital EI, diverges to 0, and they satisfy this equation. And for those who remember geometry, it's just Lie derivative of two forms. Okay, so first vector is Lie derivative of one form, second one combined. Okay, you have to divide by determinant of F, Lie derivative of two forms. Okay, we don't know why it's necessary, but it is important for now, but we'll see. So finally, for EI, capital EI, you have Helmholtz equation, like for vorticity. So indeed, I constructed sort of vorticity, artificial vorticity, geometric vorticity for, for using material cells. Okay. Just to understand again, for example, I consider just velocity field u x2 x minus x1, just rotation. Okay, the streamlines are just circles, red circles here, and then consider two lines initially. X1 is equal constant, x2 is equal constant. So we have this tangent vector E1 0, E2 0. Initially, 0 means I take this vector initially, and then they rotate. And for example, when time is equal to p over 2, they will be here. Just okay, we know how to find the evolution of this vector if I know the velocity field. Okay. Now also quite generic result. Okay, I consider two fields, K, any field, okay, and another velocity field having divergence L is equal to 0. For example, the vector EK verifies this condition. And then this identity, just if I consider KTL, it looks like helicity, but K is not necessarily velocity, then it is identity. This stuff for any scalar function G is equal LT multiplied by this stuff plus KT multiplied by this stuff. Okay, like LT multiply Lie derivative of one form of K plus gradient plus KT multiplied by Lie derivative of two forms. Okay, it's identity. So just and then I will show now for each dispersive system what is the meaning of K. I will show that for each system, K verifies this equation. Roughly speaking, Lie derivative is geometry, and gradient of something, this is force, Newton law. So physics is not geometry. So physics includes geometry plus forces, while Helmholtz equation is just geometry. Okay. Okay. And now so I put it like lemma, but theorem, but this is just a direct consequence of preceding expression. If L verify Helmholtz equation and K verifies this equation, then we have conservation law. Okay, I don't need to say okay, L is vorticity. It's just a field, geometric field, but it looks like vorticity. So, and K, it's not necessarily you will see it later. Okay, for example, for Sergey Naghdi equation, K, it's not velocity field. For example, for Green-Naghdi equations, curl, it's not a curl of U, it's curl of something, and this something will verify Helmholtz equation. Okay, so this is the main proposition, main theorem coming from just geometry and some physics, not defined because what G is. Okay, I never mentioned it. And of course, when you have conservation law of local helicity, you can say, okay, now if you have a domain with boundary S T, such that the field L is tangent to this boundary initially, then for any time it will be tangent to this boundary, and we have artificial helicity or maybe real helicity depending on the system you study. Okay. So dH of dt is equal to 0. Okay, now about application. I consider Euler, van der Waals, Korteweg fluids. People use very often just the name Euler, Korteweg, but van der Waals was first again. Okay, finally, if you read papers, okay, Korteweg did nothing in this. He just said, okay, I mean, in this field, of course. I mean, talking about Korteweg-de equation, of course. Just he wrote, okay, we can consider the stress tensor, which is function of rho, gradient rho, Laplacian, but then you have to, it was Korteweg proposition. Okay, this is why people say Korteweg theory of capillarity. But indeed, Serre showed later when you, because you have consider equilibrium of such a media, you have to consider equation divergence of the stress tensor is equal to 0. So you have 3 equations, okay, for one variable. And condition compatibility, say you after that it should come from variational principle. So finally, van der Waals. Okay, the equation are as follows. Okay, conservation of the mass, then applying variational technique, you obtain conservation of momentum, and this is why my title was not dispersive hydrodynamics by dispersive continuum mechanics, because the stress tensor is not spherical. So even if formally people say capillary fluid, nevertheless the stress tensor contains spherical part, and this is just tensor product written in strange way. You have W depends on gradient of rho. It is just the tensor product of EW, the gradient rho multiplied by gradient rho. So the stress tensor, like, and P here is just we can say variational Legendre transform. It looks like Legendre transform, but W not only function of rho, it depends on gradient rho, so classical expression of the variational derivative. And of course, because you have variational principle, you have conservation law, and I introduced here potential V, okay, right hand side, gravity over cells. It could be potential dependent on time also. Okay, so this is just general equation. And now, what is function G I mentioned to obtain helicity conservation law? This function G is here. So I can rewrite it equations of capillary fluids in the form du dt plus gradient of something. This is G, okay? So I call it here capital H, okay? So you have equation in such a form via, roughly speaking, gradient of u squared over 2 is exactly this stuff. I added and I subtracted this stuff just to have to apply my theorem, okay? So finally, if omega is curl of u, you obtain Henri equation. But if you apply this to Schrödinger equation, there's no omega, omega is 0, but you have velocity, this basis vector normalized in some sense, and I have a new theorem, new helicity, even for nonlinear Schrödinger equation. So the theorem is the following. So the equations of capillary fluids admit such a conservation law, okay? And then if you have this domain dt with special properties, so the boundary is tangent to what? It depends. Now, if you have 3D case, it should be tangent to omega, if you have 2D case, it should be tangent to this vector by definition, they're tangent. So we have Helicity integral. So we can put here instead of omega also vector EI. So new conservation laws. Okay, what I mentioned for NLS equation, omega is 0, but you have sort of analog of helicity. But for true capillary fluids, omega is classically curl of U. Okay. Now, consider the second class of models with, I call it often with models with internal inertia. So, because we are talking about bubbly fluids, Karima worked a lot on this. So, bubbles are oscillating, so there's no equilibrium between pressure outside of the bubble. Inside of the bubble, you have what people call Rayleigh length equation. Okay, so finally, this generic case, okay, W is a potential. I don't want to present expression of this potential in the case of bubbly fluids because you have to explain stuff like mass fraction, volume fraction, to write Rayleigh length equation. So it's, instead of this, I prefer to concentrate on Serre Naghdi equation, okay, because they'll understand it more easily. Okay, from general point of view, okay, derive equations for any potential W. Always mass as the constraint, conservation of momentum, and this is indeed just fluid. But pressure is not pressure on the function of rho, but it is again sort of variational Lejeune transform. P is rho, delta W or delta rho minus W. But it's like fluid because the stress tensor is spherical. And of course, this equation admits conservation of energy in such a form. If there's no external potential, it's just 0. And the energy E is written here. It is kinetic energy, rho U squared over 2 plus capital E, okay, potential. And capital E is sort of, again, Lejeune transform with respect to d rho with d. And you remember W for Serre-Naghdi equation, d rho with d term for Serre-Naghdi equation was the sign minus. So this is why when you take W minus this stuff, you obtain positive terms, so it will obtain energy which is positive. Okay, now this field K is not U, so you have to work a little bit because you have not only motion, but you have a sort of oscillation inside, micro motion. This is why vorticity is related also with micro motion in some sense. And so we have to introduce K, Q plus gradient sigma over rho, okay, with sigma given here, and the energy can be written like W plus product 0 over dt tau. Okay, what tau is partial derivative to the rho dt. Again, just general stuff, but you can obtain this equation for K. Again, you have here, as usually, Lie derivative, okay, of one form plus gradient of something. This is a new function G. So you can, for any system, formulate it in explicit form for bubbly fluids or for Serre-Naghdi equation. This function of G always prepared, always done, because we already formulated general result. Okay. So we have this concept quantity, but what omega is curl of K, not curl of U. This is different. Okay, so for capillary fluids, for nonlinear Schrödinger equations, omega, for capillary fluids, omega is not 0, but it's curl of U. Okay, but here capital omega is curl of K. So we have generalization of Helicity integral, we have such a conservative form. And again, I repeat, if you have a domain dt, special domain, where the field omega is tangential initially, then this quantity is conserved
And also, what is important, okay, you can replace, if you have 2D case, omega is 0, capital omega, because all is 2D, but you have this vector EI, okay, related with Lagrangement description of your field, and you have also new integral, even if you have 2D case. Okay, this application to Serre-Naghdi equation. W function of H and H dot. I should write here d over dt because dot is just material derivative. Given here, gh squared over 2 minus h over 6 dh over dt squared. Okay. K is given explicitly in such a form. K is u plus 1 over 3h, creating h cube divergence u. And the first person who obtained this, okay, understood K was Rick Selman, I think, maybe. Okay, Rick Selman, at least what I read in his paper, Annual Review of Fluid Mechanics, 1988, and then it also appeared in his book, and recently is Henri Gouin and Matsuno also mentioned this. Okay, so there is a physical interpretation of K. It is velocity of tangential velocity of the fluid of the free surface. So if you consider, for example, classical equations, classical formulations, Zahara formulation, and then you consider long wave approximation, so you can say, okay, this approximation of horizontal velocity on the free surface. So finally, okay, for K we have this equation in explicit form for Serre-Naghdi equations. Okay, just the last figure, just to say, okay, for Serre-Naghdi equations again, capital omega is equal to 0, but you can use this vector E alpha. So here, for example, in plain case, you have curve x1 is equal constant, x2 is equal constant, vector E2 is tangent to the coordinate line, so it's tangent to the curve x1 is equal constant. E1 is here, but U and K are not the same. So you can have velocity of the fluid, velocity K completely, maybe orthogonal and so on. And you have all this new conservational laws, generalization of helicity. And okay, so I don't know yet how we can apply this, but it's funny. So conclusion, an analog helicity integrals is found for two classes of dispersive systems of equations, gradient fluids, and fluids with internal inertia coming from Hamilton's principle of stationary action. And there is a document, okay, so preprint with remerciement, okay, to Euler. Okay, thank you.
Helicity and Kurzweil theorem were in some way related with symmetry. Yeah. How can they both be related? Or what's the so precise? What does it mean? Symmetry or how to obtain visual local symmetry. Okay, maybe I'll focus on one question. How is relabeling symmetry related to helicity? It's not answered in 1 minute. Okay, so, okay, but I mean, again, to understand better, okay, the fact what I did right is we have the equation of the net. And that is by the again, we take of the capital A. Now, if we do Lagrangement in force, why? Then we take A is equal to X over Y divide over X. And then we determine for this next one, this is the same, just you label particles.
So I give you papers, okay? You can obtain this from variational principle, but it's not one minute. No, it's not necessary. So I mean, you should, okay, variational principle, okay, just action integral is constraint. Then the question is how to use this constraint, how to integrate it. For example, one of the possibilities say, okay, I need Lagrangian coordinates, for example, and they use conservation of mass in such a form, so you can find if I vary the motion, I can find the relation. So I never use the variational principle in constraint like to add Lagrange multiplier. So there are a lot of problems, especially when you want to obtain new systems. So using Lagrange coordinates is necessary to find variation of some fiction. Time. No, the functional constraint, but constraint is another story. So, for example, no constraint, I write immediately Euler Lagrange equation. These constraints, you should understand how to vary this stuff. For example, if you do nothing and you say, okay, for example, I will vary the case of compressible fluid, relation plus divergence. Okay, let me consider a more simple case. Law which has the flow, the negative, and then say, or I will just add conservation of mass in the Lagrangement. And doing like that, and it doesn't go because you can write this in the form rules d lambda because the Lagrangement, the Lagrange equation is defined as conservative term. Then you say, okay, I will just write minus rho and this lambda is equal to gradient lambda. So it's really something potential for. So it's not good to reduce Lagrange multiplier. You have to add to obtain two Euler equations again, additional constraints like conservation of Lagrangian coordinates. But because you know the system, then you try to understand how to proceed. But if you don't know the system and you want to obtain new system, so you should invent a method based on just you spread Lagrangian coordinates and you spread variations of unknown. Other variables is a function of total displacement. Because this equation math is written like forwarding from space in Lagrange. So it's
Yeah, I should clarify that. Yeah. You say, so that, you say conservation space is symmetry, I think.
Yeah. Okay, exactly. But not a theorem that you have constraints. It was not done. In the sense, okay. So
Yeah.
it's more.
Well, then how can you relate to symmetry? And another idea to relate to symmetry.
Indeed, in my direction, I didn't care about it. I just went very direct.
Take this thing, okay? Then, okay, so look, why drugs? Okay. In particular, relative symmetry is applicable in the case of Euler equations, Gavrilyuk equations, MIT equations, but maybe not. Okay, I didn't try to do this for symmetry, no, this for dispersive equations. So, I'm not sure. I thought only relative symmetry works for Euler equations for breadth.
Yeah,
For example, say, okay, so this is the switch potential. Then you say, okay, I can add also gamma I capital E X I O T by considering equations for Lagrangement particles, equations constraints. Then you're saying the switch potential gradient of lambda plus things is gamma I, so full system is gradient of gamma I, beta I. Then I can obtain equation for gamma I should eliminate to obtain equation for U. But okay, we don't know exactly how many constraints you should introduce to obtain this Euler equation. Okay, and finally, people for Euler equations with entropy, people discuss it, and this is called the in constraint. Yes, for Euler equation in constraint. Okay, people still to say I have to add definition of Lagrangement form. And then when the people understood that it's sufficient to use only three constraints, like if you have consideration of the mass, you have consideration of entropy, if you consider whether equation is entropy, then you have just one equation for one coordinate, any velocity transported on the field. So 3 is sufficient, 4 is too much. Here, but it is how? If you don't understand, you know what you should obtain, must obtain. Then you say, okay, it's not sufficient, I add it again and again. So it's not a good method to use to add constraints and to obtain Gaussian equation. Then you don't know what you want to obtain, like ordinary model, multi-phase model, or equations of equation of the answer.
Naïki et Buddha, just written lambda O.
No,
It is not sorry.
no. I consider this local, not integral, not just general math. I have no math position locally. Each point, it's like when you consider the problem of particle mechanics, you have integral constraints and constraints. So Lagrange multiplier depends constant in the case of integral constraints, and then you have constraint which is not integral, that depends on time. So it's local equation becomes so lambda here depends on constraint. And then you do usually say, okay, all right,
I would have taken the single lambda, assigned it as a whole, and then I should have just as the volume, the total.
no? I mean, this is important, you know. You need to find a functional under this constraint. There's no method. People try to, okay, then the super do is classical mechanics. Then you have those following constraints. Okay. And then it was the beginning of 20th century, they wanted to do the same stuff for continuum mechanics. The first attempt was exactly this stuff. So I don't know what to do, but I will do like in classical mechanics. I have this constraint, I will have this Lagrange multiplier. And immediately it does work. Then Lean introduced this initial constraint and to show that this Clebsch variable for good quantity of Clebsch variable. So it's an irrational science, okay, but no, it's not tricky, it's direct, it's perfect. Lagrange mechanics, it's Korteweg, it's Korteweg. Lagrange mechanics. also the following stuff for get dynamics. Okay, you can discover it. Okay, is consider one-dimensional weather equation. Okay, then transformation weather Lagrangement is okay. Solution type is the same. While at the multi-dimensional case, equations in weather coordinates are hyperbolic, while it consider this Lagrangement variable, they're not hyperbolic because one isometric is missing. So it's quite tricky. So there's no sliding case. Have one shot to the phone. Yeah.
Have some freshmen celebrate over in the upstairs.